So one thing that I'm going to be doing every lesson in different periods is I'm going to record one Zoom a day. And so if you are absent for any reason, if even in person or a remote only person, if you are absent for any reason, I will record one lesson a day so that you can watch it and you won't have missed that material. So please know that the recordings will be available later in the day, each day. So if you are absent, you have a doctor's appointment, whatever, you could still get the material as if you were in class. Okay. So today's notes are on ionic bonding. That's our big title for today. And based on what I asked in my earlier lessons today, it seems like people weren't really sure what ionic bonding was. Does anyone in here know what it is? Not really? Daniel? Ions bonding, that's a pretty good guess. Do you know what an ion is? Okay, so we're going to get to the point where we know what an ion is, how an ion forms, and how an ion bonds. That's going to be our goals for the end of today. Okay. Before we actually talk about ionic bonding, though, we're going to talk about a rule that elements want to follow. And it's called the octet rule. The octet rule says that elements want a full outer layer of electrons in order to be stable. And by the way, to abbreviate, I just write E with a negative because that's the abbreviation for electrons. So the octet rule tells us that elements want a full outer layer of electrons to be stable. By the way, all of you at home, I do have my chat box open. If you need to ask any questions, feel free to type in the chat. What does the octet rule make you think of? What does it sound like? What do you think octet might mean? Yeah? Octagon, which means what? Oct for 8. Okay, so octagons have 8 sides. The octet rule is also based on 8. So it's the octet rule says elements want a full layer of electrons to become stable. Usually, that means 8 valence electrons. The octet rule, elements want a full outer layer of electrons to be stable. Usually, that means 8 valence electrons. I just read them, yeah. What is the exception? Which elements maybe don't need 8 valence electrons to be stable? Remember, we kind of already mentioned this. Which elements don't have 8, but they are stable? Like helium, right? Remember how helium is the exception? It only has 2 electrons, but then that first energy level is full. And so it's happy with only 2. Okay? And so you've probably all heard a name for the far right category. Do you guys know a name for them? Starts with an N. They're the noble gases. Okay? They all are gases. And they are all stable. They all fulfill the octet rule. And because of that, they don't bond with other elements in almost every circumstance. There is some exceptions. Argon and xenon sometimes bond. But for the most part, they don't because they are already chemically stable. They've already fulfilled the octet rule. And so they're noble. They don't mix with the other elements. They're happy. They're good. They don't need to mix with the common elements. The rest of the elements on a constant search to be like the noble gases. On a constant search to fulfill the octet rule. And one way they can do that is by ionic bonding. So ionic bonding happens between a metal and a non-metal. I do have an extra copy that can always be photocopied and handed out if needed. So elements gain or lose electrons in ionic bonding, and they become charged ions. And I'm going to show you how and kind of what that looks like. So we are going to draw two Bohr models, one for sodium, one for chlorine. So if you know how, you can start drawing them, kind of test your skills. We are going to be looking at the periodic table a lot today, so you can use mine or you can get yours out. So when we draw the Bohr model for sodium, how many protons does sodium have? Na. 11. And how many neutrons is the most common version of sodium going to have? Gotta look at that mass number, round it. It rounds to 23. We already have 11 protons, so we're going to need 12 neutrons. Everybody with me? How many electrons fit in the first energy level of sodium? 2. How many electrons are in the second energy level of sodium? 8. How many electrons are in the third energy level of sodium? 1. Because the third energy level is its last energy level. So this is what a Bohr model of sodium looks like. Now let's make chlorines and then we'll talk about them. How many protons does chlorine have? 17 protons. How many neutrons does it have? We look at the bottom number, which is 35, so 17 plus 18 equals 35. How many electrons in the first energy level? 2. How many electrons in the second energy level? And how many electrons in the third energy level? 7. And we can tell that because it's in the third row and it's under the 17, so that means it has 7 valence electrons. Please interrupt with questions whenever you have them. It's not interrupting. Please interject with questions. Okay. Is sodium fulfilling the octet rule? Does it have 8 valence electrons? No. Is chlorine fulfilling the octet rule? Does it have 8 valence electrons? No. But ions are formed when elements gain or lose electrons, and then they become something called ions. What if we gave away this 1 electron from sodium? Now does it fulfill the octet rule? If we take away the third energy level electron, does it now have 8? That makes it chemically stable. And so it's going to give away its electron. Now let's look at chlorine. Chlorine just needs 1 more electron, and then it would have 8, right? It has 7. If it could just get 1 more electron, it would be stable. And that's what happens. And so now I'm just going to draw the Lewis dot diagram. So for sodium, it has 1 valence electron, so we would draw 1 dot. And chlorine has 7 valence electrons, so we would draw 7 dots. And then we show that sodium can give its electron to chlorine. Gives away that electron, and it becomes happy because it now has 8 in its next layer. And chlorine gains just 1, and now it's happy because it has 8 in its outer layer. And when it gives it away, it becomes something called an ion. An ion is an element that is positive or negative because it lost electrons. Because if we look here, sodium had 11 protons and 11 neutrons. 11 positives plus 11 negatives equals 0. But now we're giving away an electron. So what is sodium's charge now? It still has 11 protons, but now it only has 10 electrons. So what is its charge going to be? Is it neutral still? It's not anymore because the protons and electrons don't cancel each other out. It's positive 1, okay? So sodium becomes positive 1 because it gave away a negative electron. So it still has 11 protons, but now it only has 10 electrons. So positive 11, negative 10 equals a positive 1 charge. It has 1 more proton than it does electron. How about for chlorine? Chlorine had 17 protons and 17 electrons, but now it has an extra. So what charge would chlorine be? Negative 1. And then opposite charges attract, so they hang out near each other, and that's ionic bonding. So elements can give away electrons to fulfill the octet rule. They can gain electrons to fulfill the octet rule. And then opposite charges attract, they hang out near each other. That's called an ionic bond. So you're going to understand this better before the end of the period, I promise. We have some vocabulary that I want you to become familiar with. Leo, are you awake? Okay. When an element loses electrons, it becomes positive. Positive ions are called cations. And that is how you pronounce it. It's called a cation. When an element gains electrons, because electrons are negative, it becomes negative. Negative ions are called anions. You don't really have to remember it because now that you've written it in your notes, you'll always be able to look at your notes if you can't remember. I'm coming with it. Yep. Don't steal my thunder on the cheesiness. That's coming next. And so what's important about ionic bonding is that opposite charges attract, so they hang out together. That is what an ionic bond is. So I'm going to write that down. I'm going to write opposite charges attract. So they hang out together. This is an ionic bond. So by the way, anyone know why I picked the 2 elements I picked for that first example? It's a compound that you all are very familiar with if you've ever put salt on or in your food. NaCl is table salt. You probably all have it in your kitchen and your dining table. That's table salt. And have you ever noticed how salt kind of looks like crystals? Well, that's because the way it forms is a positive and then a negative and a positive and a negative and a positive and negative. It makes this repeating pattern that makes a really cool crystal shape. If you don't believe me, this is a fun hands-on experiment to try at home. Dissolve some regular table salt in water, but just put a little bit of water in the cup because you're going to have to wait for the water to evaporate, so you don't want to fill the whole thing. But get a bunch of salt to dissolve in a little bit of water, and if there's still a little bit of solid salt on the bottom, add just a little bit more water and stir, 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 so it's all dissolved. It's just like gross, disgusting, salty water. Then tell your family what you're doing so no one touches it, and put it away from animals because they'll mess with it. But just let it evaporate. And when you do, the positives and negatives will line up where the positives surround the negatives surround the positives. And regular old Morton's iodized table salt, right? Just like the normal stuff, not the fancy Himalayan salts and things like that. Just like regular table salt will make really cool square crystals with like stars on them. They make this really cool crystalline structure because all ionic compounds make a crystal structure. And if you think about it, salt has just been ground down into the really tiny crystal, so it doesn't have its natural shape. But if you've ever used like other salts that are kind of bigger and they put them in the grinder for you to grind down, they kind of have a crystalline shape, and different salts, different ionic compounds make different shapes. So anyway, table salt makes a really cool one, and it's something everybody has at home. So sometimes students do that, but I always hear a story where it's like, well, I did it and I put it on my nightstand, and then my mom was mad that I had left this disgusting cup on my nightstand. Tell them what you're doing and then don't touch it. Because if you touch it when it's all evaporating, it'll mess up the crystals. But you can make your own. And because you're at home, using something from your kitchen and hopefully a glass that was clean, you can then put that salt on your food, right? It's totally edible. It's chemically the exact same thing, it's just in a different shape. So, fun facts with Leavenite. All right, so what if you're trying to remember the words cation and anion? Well, I can't disappoint. I have some cheesy ways to help you remember these. So we'll start with the non-cheesy one. This is the easy one. If you're trying to remember anion and you don't like cheesy, dumb things, nope. You can write one or both if it would help you remember, or none. An anion is a negative ion. Kind of helpful, right? It's a way of kind of remembering the word. Or if you're into cute things like I am, I have this little friend, and his name is Leo, the cation. Can you tell he was a cat? Yeah, okay. So his name is Leo, the cation, but his name actually means something. His name helps me remember how he's formed. So Leo is formed because he loses electrons only to become a cation. And it doesn't stop there, people. Leo, the cation, is positive. So we draw some of those. And now in the future, you're going to be like, you can't remember what a cation ion is. And I'm going to be like, Leo is positive. And I'm going to do that all the time. So that is how I first remembered them when I learned these vocabulary terms and didn't want to mess them up as a teacher. And eventually I got confident enough to just share my weird thinking. So there you go. Leo, the cation. I added the positive part myself. Maybe people have copied me since, but I'm pretty sure I invented it. Okay. We're going to take some, just write down 3 simple rules for ionic bonding, and then we're going to practice. And by the end of the period, you are going to be doing the world's most complicated ionic bonding problems because you're smart. I'm not even joking. You will be doing the most complicated problem. And you are smart. As long as I don't run out of time. I got time. Do I have half an hour? No. I have 15 minutes. I think we could do this in 15 minutes. Okay. Steps. You need to write this down for sure. Steps for ionic bonding. Woo! Number 1. Show electron movement. Step number 1 is show the electron movement. So let's do an example. Let's do magnesium and oxygen this time. How many valence electrons would we draw for the Lewis dot diagram of magnesium? 2. Good job. How many valence electrons would we draw for the Lewis dot diagram of oxygen? 6. If you ever have a question on how we're getting something, speak up. Let me know. Okay, so we know that they want to follow the octet rule. Are either of these elements following the octet rule? No. And I'm going to give you a hint. They always do the smaller number. So here's my question. Is magnesium going to lose 2 or gain 6? What's the smaller number? It's going to lose 2. Is oxygen going to lose 6 or gain 2? Smaller number, it's going to gain 2. Okay, so to show the electron movement, magnesium can give away its 2 electrons, and oxygen can take its 2 electrons. Is magnesium happy now? Yes, because its layer underneath will now be fulfilling the octet rule. Is oxygen happy now? Yes, because it had 6 and it got 2 more, so it is happy. Questions? Okay, that's step 1. The video is, you can also take pictures of my notes. I guess I could post them if it would be helpful. But here's what I'm going to do. I'm going to start posting differently. I'm not going to post every single day. I will post a document that says like 4-day in-person learning, April through June. And then I'll add to that document. So I could add a link to this picture in that document. But I'm not going to make daily assignments that people have to constantly mark as done. Does that make sense? So I'll show you. I'll show you tomorrow when I make it. So the second step is to write each ion with its charge. So when magnesium loses 2 electrons, what is its charge? Positive what? Positive 2. When you lose 2, you become positive 2. If you lose 7, you'd be positive 7, but that doesn't happen. The most you can lose is 4. Most you can gain is 4 as well. Okay, oxygen, it gains 2 electrons. So what is its charge? Negative 2. It got 2 extra negative electrons, so it has a charge of negative 2. Last step is to write the chemical formula. Cation first, anion comes second. And so the chemical formula is where we write the elements and we show how many of each of them there is. And magnesium came first, and there was only 1, and we don't usually write the 1. We write it if it's 2 or more. And oxygen comes second, so we just write MgO. Let's try a problem together. Let's try strontium and fluoride. So I want you to do as many steps without me as you can. Leave me in the dust. So start by writing the Lewis dot diagrams for these 2 elements. How many dots does strontium get? Element 38. How many dots? 2, good. How many dots does fluorine get? 7. So does strontium want to lose 2 or gain 6? Lose 2. Does fluorine want to lose 7 or gain 1? This is going to be interesting. Okay, so strontium gave an electron to fluorine. Is strontium happy? No, because it hasn't lost enough. Is fluorine happy? Yes. So the cool thing about ionic bonding is you can add another one of these elements if you need it until everybody's happy. So here's another fluorine. And strontium can give its electron to the other fluorine. I'm only allowed to use those 2 elements, but I can use the number that I need to make everybody happy, because that's what happens in the world, in the atom world. So step 1 was showing the electron movement. Step 2 is writing each ion with its charge. So for this strontium, how many electrons did it lose? So what's its charge? Plus 2, because it lost 2. How many electrons did this fluorine gain? 1, so it's fluorine minus 1. How many electrons did this fluorine gain? 1, so it's fluorine minus 1. And notice I write my fluorine so that they're kind of touching strontium, because in the real world they would. The negatives would surround the positive. So it's better to write the F's on any of the sides of strontium. That's better than writing two F's next to each other. So I just always try to do it the more correct way. You're not turning in anything handwritten, but as long as you've drawn them, you're good. All right, last step is to write the chemical formula. The cation comes first, so the positive thing comes first. So strontium comes first. We only had one strontium, so we just write Sr. And then we write F, and what number do we write after F? The little subscript of a 2. It's the small number on the bottom. You've all seen H2O for water, right? So good question. We added the second F when we realized that strontium gave away one of its electrons, and it still had another one to give. So you're allowed to add another of the elements that you're working with if you need to. And we're going to do another example, so you'll see that again in this next one. All right. We're going to finish early, guys. I only had 2 more examples for us to do. Let's try potassium and phosphorus. So K and P. And again, feel free to leave me in the dust. Start doing the steps. Start by doing the Lewis dot diagram. How many dots for potassium? How many for phosphorus? 5. So potassium's going to want to lose 1. So that's cool. I can give it to phosphorus. Is phosphorus happy, though? No. Phosphorus still needs to gain 2 more, right, to get to 8. So again, we can add more of the elements we're working with until everybody's happy. So I've added 2 more potassiums because phosphorus needed to gain 3, and each potassium was only giving away 1. Questions? Is everybody happy in this picture? Each potassium got to give away 1, and the phosphorus got the 3 that it needed. Okay. Next step is to write the elements with their charges. So go ahead and try that. So P had a -3 because it got 3 extra negative electrons. And each potassium had a +1 because each potassium lost 1. And again, I'm drawing the potassiums kind of surrounding the phosphorus because that's what would happen for the chemical. Because opposite charges attract. And then the last step is writing the chemical formula. I had 3 potassiums. I had 1 phosphorus. So it looks like this. You guys ready to do the hardest problem that I could give you? Literally, not even exaggerating. Here it is. I want you to do aluminum and selenium. Doesn't get any harder than this. This is a little tricky. Al and Se. Al is element 13 and Se is 34. How many valence electrons do we draw for aluminum? 3. How about selenium? 6. So aluminum can give 2 electrons to selenium, and selenium is happy. But is aluminum happy? No. So we're going to need another another selenium to take aluminum's electrons. So aluminum can give away its last electron, and now aluminum's happy. But is this selenium happy? No. So we must need another aluminum. So now that selenium's happy because it got its second electron. But now this aluminum isn't happy. So we add another selenium. And then it all works out. Because this aluminum can give 2, And now every aluminum has lost 3. Every selenium has gained 2. This is truly as hard as it gets. So when we write our elements with their charges, each aluminum is +3, selenium is -2. I try to kind of write them in a way where the seleniums are all surrounding aluminums and the aluminums are all surrounding seleniums. And what? It's as hard as it gets. So it's not that hard. And I like things that are not that hard but make me sound smart. I don't know about you, but it just makes me feel good about myself. All right, so go ahead and write the chemical formula. We'll see if you got it right, and then we're done for today. So did you write Al2 Se3? Because you're counting how many of each element you needed. Tomorrow we are going to practice this. Thursday we're going to have a homework quiz on it. Bye, Zoomers.
Bye, thank you.
Yeah. If anyone wants to take a picture of my notes, you're also welcome to do that. They're available.
By the way, you're still recording.
What'd you say?
You were still recording.
Oh, thank you. I will stop recording.